You're 35,000 feet in the air, cruising at 500 miles per hour, sipping your coffee, and you glance out the window. It's small, it's oval, and you've probably never once asked yourself, why? Why not a big, beautiful rectangle? More light, better views, happier passengers. Seems obvious, right? Airlines want you comfortable, so why would they shrink the windows and curve the edges? Turns out, the answer involves one of the deadliest aviation disasters in history. A physics concept so elegant it appears everywhere in nature, and an engineering lesson that quite literally changed the shape of the modern world. Buckle up. The golden age and the tragedy. To understand why airplane windows are round, we need to go back to the early 1950s. The golden age of aviation. The de Havilland Comet had just launched as the world's first commercial jet airliner. It was a technological marvel, faster than anything before it, quieter, more comfortable. It could carry passengers across continents in hours instead of days. Britain was proud. The world was watching. Passengers loved it. Airlines ordered more. The future of air travel had arrived. But within just 2 years, 3 comets mysteriously exploded mid-flight. No warning, no distress call, no survivors, just wreckage raining into the ocean. The world was stunned. What was killing these planes? Investigators launched one of the most thorough accident investigations in aviation history. They reassembled wreckage piece by piece. They pressurized test fuselages in giant water tanks, using water instead of air so that any failure wouldn't be explosive. They ran thousands of simulated flights in a matter of weeks, and eventually, they found the answer. It was almost too simple to believe. The windows were square. More precisely, they were square-cornered, and those corners were quietly, invisibly, silently tearing the plane apart from the inside out, one flight at a time. The science. Here's the physics, and I promise it's fascinating. At cruising altitude, the air outside is incredibly thin, about a quarter of the density at sea level. If you opened a door up there, you'd lose consciousness in seconds. So, the cabin is pressurized, pumped full of air to keep you breathing, thinking, and alive. That pressure difference between inside and outside creates enormous outward force on every single surface of the aircraft. The walls, the floor, the ceiling, and especially the windows. Now, stress is not static. It moves through metal like water flowing through a landscape, spreading out, finding paths, looking for somewhere to go. A circular or oval opening handles this beautifully. The stress flows around the curve evenly, distributed across the entire edge. No single point bears more than any other. It's balanced. It's elegant. A sharp corner? That's a completely different story. Corners are where stress piles up. The mathematics of it are brutal. At a sharp 90-degree corner, stress can concentrate to 3 times the level of the surrounding material. Sometimes more, depending on the geometry. Engineers have a name for this: stress concentration. And every time that airplane pressurized on the way up and depressurized on the way down, every single flight, every single cycle, those corners were being bent back and forth, microscopically, invisibly. The metal was accumulating invisible damage, flight after flight after flight. This is called metal fatigue. The metal doesn't break immediately. It weakens gradually, like bending a paperclip back and forth until it snaps. You can't see it happening. You can't feel it, but it's happening. On the Comet, the square corners of the windows eventually cracked, tiny hairline fractures. And at 35,000 feet, with enormous pressure pushing outward, those cracks didn't stay small. They propagated, spread instantly across the fuselage, and the entire aircraft tore apart in a fraction of a second. The passengers never knew what hit them, because nothing hit them. The plane simply came apart. The fix and the legacy. The aviation industry didn't just mourn, it studied, it redesigned, and it moved fast. Engineers eliminated square corners entirely. Windows became oval, elliptical shapes where stress flows smoothly around every edge, with no corner to ambush it. They also changed manufacturing methods. Holes in the fuselage were drilled rather than punched to avoid introducing micro cracks from the start. Window frames were reinforced, Surrounding fuselage panels were strengthened, and modern aircraft now undergo extraordinary testing before a single passenger boards. Thousands of pressurization cycles, stress measurements at every rivet, fatigue testing that simulates decades of flight in controlled conditions. That small oval window you barely notice. It is the direct result of tragedy, relentless investigation, and one of the most important engineering corrections in the history of transportation.